Hello everyone, I'm Afshin. My advisor is Dr. Mubarak Shah. Thank you very much for joining my presentation, which is the work that I've done during my PhD, and it's titled Global Data Association for Multiple Pedestrian Tracking. So the problem that I'm trying to solve is multi-target tracking, where the goal is to automatically detect and track every individual in a video sequence and then assign an ID to every person. So we would like this ID to remain the same for the person throughout the entire sequence. Most previous multi-target tracking method, they divide the problem into two sub-problems. First, they apply a pre-trained object detector on frames of a video sequence to get the object hypothesis, as you can see on the top video. And once you have the object hypothesis, the problem of tracking narrows down to linking the detections that belong to the same target and assigning an ID to every individual. So this step is called data association, and the focus of most previous multi-object tracking methods has been in designing a better data association technique, so as the first two sections of this dissertation. Tracking is an old problem and it's been studied for decades. However, it's still considered as an unsolved problem due to several challenges. Probably the biggest challenge is having noisy detection input. This challenge and this noise could be due to several reasons, such as occlusion. When you have targets which are occluded, it's most likely most object detection method would fail to localize the targets. And another reason is having targets that go under heavy articulation, which happens mostly in sport sequences. The other challenge for most trackers is having a cluttered background. If you have targets that move, that are very similar and are moving very close to each other, that may confuse as many trackers. And another challenge is abrupt motion, because most multi-target tracking methods assume a prior motion model for the targets that they are tracking. And if you have targets that don't follow that motion model, it causes a lot of trouble for trackers to follow that person. So now let's have a mention of few applications of multi-target tracking. It has a lot of application in medical imaging. You can use multi-target tracking method to track cells, which eventually help doctors to diagnose diseases. It has applications in sport analysis, where you can track sport players and you can provide stats of the game and players to the audiences and coach. It has applications in human-computer interaction, where you can track fingers, hands, and gestures, and it actually can bridge the gap between human and computers. But most important application of tracking, which is the focus of this dissertation, is undoubtedly surveillance. But why surveillance is so important? Because today there's over 30 million cameras in the United States. Everywhere you walk in a shopping mall, in an airport, or even in a private store, you've been constantly watched. These cameras record over 4 billion hours of videos every week. So it's obvious that manual supervision of these videos is impossible, and it's very needed to be able to automatically analyze such videos. And the key to automatic analysis of these videos is multi-target tracking. Here's the outline of this presentation. In the first two chapters, we proposed two new data association methods, and we proposed two new trackers. One is called GMCP, the other one is called GMMCP. And in the last chapter, we're going to focus on tracking targets in crowded sequences. The first part of this presentation, which is GMCP tracker, is published in ECCV 2012 and has received a lot of attention. And there's a key difference between this new data association technique with respect to previous one. Most previous data association methods, such as bipartite matching, they are temporally local, which means that they only consider two or few frames during data association. For example, bipartite matching is a very good example of that I'm showing in the slide. In bipartite matching, you consider only two frames during association. You create the bipartite graph between two frames of a sequence, and you can solve the association problem jointly for all the targets. However, in GMCP, we are not temporally local, but we are temporally global, which means that instead of two frames, we consider many more frames during data association. And instead of having a bipartite graph, we have a k-partite complete graph. And now, track of a person is going to form a clique in this complete graph, as it's shown in red. So you see the k-partite complete graph with gray edges, and you see a track of a person which is forming a clique in red. So the goal of GMCP is to find these cliques for you. Basically, GMCP is going to find the best clique in this complete graph that has the least cost, and this clique is going to represent the track of a person. Once we find one track, we're going to remove it from the graph. We're going to solve GMCP again to find other tracks in the sequence. Here's the pipeline. Given a raw input sequence, we apply a pre-trained object detector on every frame to get the object candidates. Then we divide the sequence into batches. Every batch is going to have few frames, let's say 50 frames in it, and we're going to use GMCP matching to get the tracks in every batch. As you can see, since batches have few frames in them, these tracks are going to be very short tracks, and we're going to call these small tracks Tracklet. So these Tracklets, in order to get the final trajectories, we need another level of data association, and for that we're going to again use GMCP to connect these Tracklets and form the full trajectories of targets. Now I'm going to show you how do we form these Tracklets. First we need to create a graph. We have few frames and we have detections in those frames. Each frame is going to form a cluster, and each detection in each frame is going to be the nodes within that cluster. Once we have the cluster and the nodes, we're going to form the graph. Each two nodes in two different clusters are connected through an edge, and that edge is going to have a weight. So this weight is going to capture the appearance similarity of two nodes in two different clusters, and it's nothing but the sum of histogram intersection between the body parts of two people in two different clusters. Once we have the complete graph, the goal of GMCP is to find one subgraph by selecting exactly one node from every cluster that has the least cost across all the subgraphs in this complete graph. So after solving GMCP, this is the subgraph that we're going to get, and the appearance cost of this clique is shown here, which is the sum of the edge weights. So as you can see, GMCP has selected one node from every cluster, even if the person is not present. For example, in frame 3 and 4, the person was not there. It still selected two other nodes that minimize the cost of that clique, and we're going to talk about how do we handle these outliers later throughout the presentation. The objective function that GMCP minimizes doesn't only have the appearance information, but also has the motion information, and alpha is the weight of the motion. So for motion, we just simply use a linear motion model, because for a short period of time, you can assume that targets move with constant velocity. So the problem here is that what if a person is not detected in a frame? And we said that GMCP is going to select one node from every cluster. So in this example, you see that person is not present in 3 frames here. So GMCP is going to select 3 other nodes that don't belong to this person as a track of this person. And once we remove them, that means we're going to remove nodes that don't belong to this target. So we have to be able to handle these cases. So for that, we're going to introduce hypothetical node. So we're going to add one hypothetical node to every cluster, and these hypothetical nodes are selected whenever there's not a reliable candidate for that person within that cluster. So these hypothetical nodes are treated exactly as the regular node. They have a location and they have an appearance. For location, this is how we're going to localize it. We're going to, after a few iterations in GMCP, we're going to fit a line to the feasible solution found by GMCP. And the goal is to maximize the number of inliers. And the inliers are the points within the feasible solution that have a distance smaller than delta to the line. And once we find the light, any point that has distance greater than delta are going to be detected as outliers, and we're going to remove them from the solution. So this is how we're going to locate the hypothetical node, which is based on the parameter of the line. And appearance of hypothetical node are the average appearance of the inliers within that solution. Here you can see after placing the hypothetical node, we were able to remove the outliers in frame 3 and 4 and place the hypothetical node in the right location to get a nice track for that person. Now the question is that how do we solve GMCP? Before that, let's define the concept of neighbor solution. Two solutions are neighbor if they're identical except in one element. In GMCP, two solutions are neighbor if they're identical except in one element of one cluster. For example, here you can see two neighbor solutions for GMCP. You can see that the nodes in all the cluster are the same except the nodes in the first cluster. So these are two neighbor solutions. And here is the detailed algorithm for GMCP, which is based on local neighborhood search. We start with an initial solution, and we mark it as current solution. Then we find all the neighboring solution to the current solution, and the one that induces a lower cost is going to replace the current solution. And we're going to do that until we converge. In order to avoid getting stuck in local minimas, we use taboo search, which is a variation of local neighborhood search, and gives us better results. We implemented GMCP in MATLAB, and a non-optimized MATLAB code on a quad-core machine takes about 4.4 seconds to process one frame. Here I'm going to show how this works on 50 frame of town center sequence. Here you see the sequence, and here you see the object detection bounding boxes, and the red dots are the center of those object detection. I've overlaid the first and last frame of this sequence, and these are the center of all the human detections. GMCP is going to start with a random solution. You can see the iteration on the top. As we go through the iteration, the solution is going to improve until it converges to a track of one person. as you can see here. Once we find the first tracklet, we're going to remove all the nodes and edges belong to that person, and we're going to solve the optimization again until we find the second tracklet. And we do this until there is no tracklet left in the sequence. So one thing I want you to focus is that this person entering the scene. In the beginning, we are missing a lot of detection for this person. And I'm going to show you how hypothetical nodes are used to fill the gap and actually make a nice tracklet for that person. So I'm going to zoom in that person, and you're going to see exactly how the hypothetical node through iteration are placed to fill the gap for that person. So the hypothetical nodes are shown with crosses, and the real nodes are shown with circles. Now let's see some more tracklets for that sequence. I'm going to show you 6 tracklets for town center sequence. You see that there is no association between tracklets in different segments because we solve GMCP for each segment independently. Another thing that I want you to focus is that when sometimes we are missing tracklets for a person. For example, this lady who is walking with a baby, since there is occlusion, we are missing a complete tracklet for this person. So in the next level of data association, we also need to have a global method to be able to handle these kind of occlusions. Again, that's another level of data association to connect the tracklet and form the full trajectories. For that, we're going to again use GMCP. Each tracklet in every segment is going to be one node. And that tracklet, the average location is going to be the location of the node, and the average appearance is going to be the appearance of the node. We use GMCP, we form the full trajectories. Here's an example of parking lot sequence. You can see that person is going behind the car, and we are missing one tracklet for that person. But after the merging, the hypothetical tracklet is placed in the right location to give a nice trajectory for that person. And this is the results on the sequence I showed earlier. You see that we were missing 2 tracklets here, and we were missing 1 tracklet here. But after merging, those gaps were filled, and we're getting nice tracklets. Let's have a look at some more results. This is the PET sequence. It has a little bit over 700 frames. The challenge here is that targets are moving with nonlinear motion. So the assumption of linear motion model might not be valid for long term. So we have segments with fewer frames. We consider only 15 frames for segments of this sequence. And here we are going to we're comparing our results, which is top right, with 3 other best published methods at that time. Whenever you see a red arrow, it's whenever an ID switch happens, and you can see that the number of red arrows in our method is far fewer compared to other methods. And here's the results on town center sequence with the best published method at that time. You see that on the left it's missing 2 targets, but the 2 targets are recovered on the right. Here's the results on parking lot sequence that I showed you earlier. This sequence is challenging because you have targets with similar appearance, and they are constantly occluding each other, and you have this long-term occlusion that I talked about earlier. That person goes behind the car, but we are able to retain the ID for that person throughout the video. For quantitative evaluation, we use clear metrics as well as trajectory-based metrics. MOTA, multiple object tracking accuracy, takes into account false positive, false negative, and ID switches. MOTP consider the tightness of bounding boxes with respect to ground truth. We have mostly tracked, that tells you the percentage of the track that are successfully tracked over 80%. Mostly lost is the percentage of tracks that are successfully tracked less than 20%. We have ID switch, we have multiple object detection accuracy, and multiple object detection precision. So some of these measures we want them to be high, such as MOTA and MT, and some of them we want to be low, such as mostly loss and ID switch, and we're going to use them interchangeably depending on what method we are comparing against. But our focus is going to be mostly on MOTA, mostly track, and ID switches, and also mostly loss, because the other really depends on the underlying human detection that you're using and don't really capture the tracking performance. This is the town center sequence. You can see that we improved MOTA by almost 9% in the sequence compared to previous methods. Here's 3 other sequences. We improved both MOTA and ID switches. Okay, so we talked about GMCP and how nice this method is, that it gives good results, but we haven't talked about the limitation of this method. One thing that you might have already noticed is that GMCP finds tracks one by one, which is not the case in optimal scenario, because you want all the people to be able to compete for the available detections at the same time. So joint optimization is what you're looking for and you want to have in a tracking system. We use a greedy optimization for GMCP, so it's not going to give you the optimal solution for sure. It may get stuck in local minimas. So we want to see if we can do better or not. And GMCP is slow. It takes about 4.4 seconds to process every frame, which is not suitable in all the applications. So we want to see if we can try and do better than what we already have. And this leads us to the second section of this presentation, which we propose GMMCP tracker, which is a modification over GMCP. This work is published in CVPR 2015, and here's the main idea behind it. So you saw this figure before. This is the k-partite complete graph, and this is the solution that GMCP is going to give us. Now we want to see if we can find all these cliques at the same time. Basically, we want to see if we can find all the k cliques here, 3 targets, all the 3 cliques at the same time, as you can see on the right, because this is the case in optimal scenario. And we say, yes, this is possible. So thus, we propose an improved version of GMCP, which is called Generalized Maximum Multi-Clique Problem, that is going to find multiple cliques at the same time for us. Here, I'm going to highlight the differences between GMCP and GMMCP. GMCP doesn't have a joint optimization, while GMMCP enjoys a joint optimization framework. GMCP, we followed a greedy optimization for that. We proposed another optimization for GMMCP, which is able to give you high-quality solution. GMCP is slow, but GMMCP, the optimization itself is very fast, and it gives you results close to real time. Here's the framework. We start with human detection every frame, similar to GMCP. The next step we have is that we get a set of low-level tracklets. These low-level tracklets are very tiny tracklets that have the maximum length of 10 and minimum length of 5, and they are obtained by just simply considering the overlap between two detections in 2 consecutive frames. And I'm going to tell you why this is important. Then we feed this to GMMCP, and we get tracklets that are a little bit longer, and we call them mid-level tracklets. Again, we feed them to GMMCP, and we get the final trajectories, as you can see on the bottom right. So here is how we get the mid-level tracklets. We have few segments, and in each segment we have the low-level tracklets that are very tiny tracklets shown here. And the reason we start with low-level tracklets are bifold. First of all, if you start with low-level tracklets, you're going to be able to incorporate motion information in the edge weight of the graph, which was not the case in GMCP. The other reason is that you can reduce the computational complexity, because now instead of having 60 frames, you only have 6 segments, which is very helpful. So how do we solve it? We first create the clusters. Every segment is going to be 1 cluster, and the low-level tracklets are going to be the nodes within the cluster. We form the k-partite complete graph, where there's an edge between 2 nodes in 2 clusters, and each edge is going to have a weight, and the weight is the combination of appearance and motion. And nu defines the importance of each weight. For appearance, we again use histogram intersection between color histogram of 2 low-level tracklets, and we have the global linear motion model, same as GMCP. Now, what GMMCP is going to do is that it's going to find k cliques simultaneously by selecting exactly k nodes from every cluster. And you can see the results of that here. So here we have selected 3 cliques at the same time, and you can see the results one by one here. And whenever the person was not present, we put dummy nodes to fill the gaps, and we're going to talk about them. How do we select these dummy nodes? This is the first tracklet, second tracklet, and third tracklet. And all 3 of them are found at the same time. For optimization, here's how we do the optimization. First of all, GMMCP is an NP-hard problem. It's not difficult to show that GMCP reduces to GMMCP. GMCP is a known NP-hard problem, thus GMMCP becomes NP-hard too. When dealing with such problem, most methods, they follow an approximate solution for that. But what we do, we instead propose a binary integer programming for GMMCP. Before getting into details, let's define the notations. Vij is a binary variable which defines the ith node in the jth cluster. Eijmn is the edge between 2 nodes in 2 different clusters, and h is the number of clusters. Here's the objective function. We try to minimize C transpose X. C is a long vector that has the weight of all the nodes and all the edges in the graph. And X is also a long vector that has a binary variable for each node and each edge in it. And we have to define a set of equality and inequality constraints to make sure that the solution found out of this optimization is a valid solution to GMMCP. The first constraint is going to ensure that we select exactly k nodes from every cluster. So the sum of the nodes in every cluster is going to be equal to k. The second constraint is going to tell us that if you select one node, you have to select exactly h minus 1 edges connected to that node. And the last constraint is telling us, or is ensuring, that the solution found by this optimization is going to form a clique. Basically, if you select two edges that have a mutual node at one end, you have to make sure that the other edge is also selected. But what if we don't have low-level tracklets in all the segments, which was the same case with GMCP2? What we do is that we propose dummy nodes, and dummy nodes are treated exactly the same as regular nodes, but these dummy nodes have fixed weight for the edges connecting them to all the other nodes in the graph. And this edge weight has been found through experiments. And whenever there is not a confident node for a clique in a cluster, these dummy nodes are selected instead. But now the question is that how many dummy nodes do we have to add to every cluster? So we can find the upper bound to the number of dummy nodes that we can add to every cluster to make sure we never run out of dummy nodes. But again, GMMCP is a difficult problem to solve, and the more nodes you add, the more you increase to the computational complexity. So we want to see if there's a smarter way of doing this. So we did that through aggregated dummy nodes. The idea here is that we want to replace all the dummy nodes in every cluster with one super dummy node that we call it aggregated dummy node that is shown on the right. So now ADNs are no longer binary variables because you have to allow them to be selected multiple times by multiple clicks if needed. So this requires a new formulation because now we have binary variables and we have integer variables. So this requires a mixed binary integer programming solution, and we have to make slight changes to the constraints that we have. The first constraint remained the same as the one that we had before, which ensures that the solution is going to form a clique. The second constraint is telling us that the sum of outgoing edges of a node and entering a cluster should be equal or less than 1. And the last constraint is ensuring that exactly k nodes from every cluster is selected. Now let's see how does these dummy node help us with the runtime. So I'm going to show you now the runtime of GMCP, which you can see here with respect to different number of frames in a batch. You can see that the runtime increases slightly. GMMCP without ADN, this is the runtime for that. And once we add ADNs, we can improve the runtime significantly. And this is the runtime for another sequence. And this is the runtime with respect to the number of targets in the sequence when the batch size is set to 50. You can see that GMCP takes in average 123 seconds to solve the association for one segment, while GMMCP with aggregated dummy node takes less than 2 seconds to solve the association for 50 frames. Now let's have a look at some qualitative results. On the left you see the mid-level tracklets for this sequence, and on the right you see the full trajectories found by GMMCP. We introduced two new data sets and we annotated targets in them. One is this sequence that you see. It's a kind of crowded sequence with a lot of inter-object occlusion, and the frame rate is also low, and we show later that we do better in numbers. And here is the other sequence that we presented with this paper, which is parking lot 2 sequence. It's interesting because there's a fighting scene happening. We have nonlinear motion, we have occlusion, we have target with similar appearance. That's kind of make it challenging tracking sequence. And now let's have a look at some of the occlusion handling capability of GMMCP in town center sequence as well as parking lot. This was parking lot sequence. If you look at object number 12, you can see that it's going on the long-term occlusion, and we are able to keep the ID for that person. And whenever we don't have detection, we are interpolating the bounding boxes. And here's town center sequence. There are a lot of short-term occlusion. There's a bench here that's occluding the people, but you can see that for most cases we can do pretty well. Some more example on town center sequence. Now let's have a look at the numbers. You can see that for most sequences, actually for all of them, we improve MOT A, and for most sequences we reduce the number of ID switches. Sometimes the number of ID switches of GMCP is slightly lower than us, while we improve other metrics, and our method is still faster than GMCP. These are the two new sequences. You see that here GMCP is doing a little bit better in the number of ID switches, but we improve mostly track and MOT A significantly. So talking about GMCP and GMMCP tracker, I don't know if you have noticed or not, most sequences that we considered here, the number of targets are limited to a few dozen. So we are not dealing with sequences with a lot of targets. What's going to happen if we move on to sequences with this? where there are hundreds of targets that you're interested in tracking. This happens a lot in marathon sequences, religious riot, political rallies. You have a lot of people that you're interested in safety of these scenarios, and multi-target tracking is very essential in those cases. So this kind of sequences leads us to the last section of this presentation, where we're going to focus on tracking hundreds of targets in high-density crowd sequences. This work is submitted to IEEE PAMI, and the PDF is available on arXiv. There are several challenges that make this problem difficult. The first thing is that pre-trained object detectors fail to localize targets in these sequences. This is mainly to the due to the camera viewpoint. These sequences are captured cameras facing down, where you can see the full body of targets, and also face and head detectors also have shown low performance on these sequences. The other challenge is small apparent target size. The targets are very tiny, and it's very hard to extract useful appearance information to be able to distinguish target from each other or from the background. And the other challenge is the large number of targets that you want to track. So this extremely increases the computational complexity that becomes a big challenge to handle. This area of research hasn't been studied that much, and we are only limited to a handful of methods. So probably the early work of Ali and Shaw is the first example of such methods. This tracker doesn't have a joint optimization, which means that it tracks target one by one, mostly because it wants to reduce the computational complexity. It does capture interaction, because interaction is very important in crowded sequences, and it does that through learning the crowd flow in a sequence. It does require learning, which is not a good thing, because if you change the sequence, you have to do the learning again to learn the prior motion. And it cannot handle anomalies in the scene, because if you have targets that move against the crowd flow, you won't be able to track them. The work of Idris et al., which was published in IVC 2013, is a newer example of such methods. This method also doesn't have a joint optimization. It does capture interaction by learning the neighborhood motion. It doesn't require learning, which is a plus, but the method by itself cannot handle anomalies. It depends on some heuristics, such as instantaneous flows, to handle the anomalies, which is not good. And the work of Bera et al. Is another example of such methods. It doesn't again have joint optimization, mostly due to complexity. It doesn't capture interaction, but it doesn't require learning, and it can handle anomalies, which are pluses. What we want to do here is that we want to have a method which has a joint optimization, because that's very important. We want to be able to capture interaction. We want to have a method that doesn't require learning, and we want to be able to handle anomalies too. We consider a set of constraints in our formulation. The first one is the spatial proximity constraint. If you look at this frame here, and if you focus on that red box that I'm showing here, you see a lot of targets that look very similar. This is going to confuse most trackers, especially these targets are very close, they look very similar, so it's very likely that trackers drift away from one and jump into the other one. So what we do to handle these cases, we're going to consider the spatial relationship between targets, and we're going to encourage the trackers to select candidates that are not too close to each other. The other term that we consider in our optimization is neighborhood motion effect, because neighborhood information is very valuable in crowded scenes. If you have targets such as the one that we are showing with a yellow ellipse, you can see that its neighbor can probably provide you very strong cues about the location of the target. For example, if that person gets occluded or the appearance is low, you can most likely localize that person through her neighbors. And the last constraint is grouping constraint. This constraint hasn't been incorporated in a crowd tracking method before. And the idea here is that you want to find groups, and you want to encourage the people in a group to keep the formation for a short period of time. So considering all these factors, appearance, motion, neighborhood motion, spatial proximity constraint, grouping constraint, we want to bring them all into one single formulation, and we do that through binary quadratic programming. We propose a binary quadratic programming that takes into account all these terms together and also enjoys from a joint optimization framework. I'm going to show you the idea here for only two targets to make it easy. Imagine you have these two targets shown on the right, and these are the candidate location for each target, that each can potentially represent the new location of the target in that frame. For each location, you're going to consider a variable xij. I is the index of target, and j is the index of the candidate for that person. And each candidate is going to come with a cost. And for simplicity, let's assume that this cost is nothing but the appearance similarity. Let's say you compute some color histogram similarity between the candidate location and the template of that target to get this cost. And given this location, C and X, now the goal is to find the best set of candidates that maximize an objective function shown here. C is a long vector that has the appearance cost for each location, and X is again another long vector that has the variable for all the candidate location. In order to make sure the solution is a valid solution to tracking, first you need to put this constraint that each variable is a binary variable, because you don't want to assign one location to two targets. The other constraint is telling you that the sum of variables for every target is going to be equal to 1, because you want to select exactly one location for every target in that frame. However, our formulation is not limited to only appearance term. It has the target motion term, it has the neighborhood target motion in it, it has the spatial proximity constraint, and it has the grouping constraint in it as well. So the first three terms are going to be the linear terms in our objective function, and the last two terms are going to form the quadratic terms in our objective function, because for grouping and spatial constraint you need to consider the pairwise relationship between the targets. And the two constraints remain the same. Now let's see how do we get the affinity measures for this formulation. For appearance, we train a regressor for every target, giving the template and the labels, then minimize the objective function shown here, and getting the model for every target, you can get the appearance cost using this equation here. Most previous multi-target crowd tracking method, actually all of them, they use a generative tracker as baseline. We did a study in 2013 that is published in PAMI that discriminatively learned tracker works much better than generative model, and we're going to show that in our experiment too. For neighborhood motion, first we're going to find groups of people with coherent motion. Here you can see that groups of people that have similar type of motion, this is achieved by clustering the trajectories of target. And once we have these groups, we're going to find the neighborhood motion cost using the equation shown here. So CI is the cost for target candidate I, and Sij is the location of candidate I, and Pj is the speed of the neighborhood J. Each neighbor is going to have a weight associated to that, and this weight depends on the distance of the neighbor from the target that is obtained from here. So the closer the neighbor is to the target, the more effect it's going to have on the target. For quadratic cost, this is the equation for getting the spatial proximity constraint. Given two candidate location, the closer they are, the higher cost you want to pay. However, if you use the matrix S by itself, this S is not going to be positive semi-definite, so it's going to make your optimization non-convex. So what we do instead, we take the normalized Laplace matrix. This trick is going to have the same effect as what we want, but at the same time, CSP is going to be PSD now. For grouping constraint, we cluster the trajectories to find the groups, and once we find the groups, we're going to form the minimum spanning tree for the targets within each group, as shown here. And the parameters of this tree is going to have the group information, and this is how we get the cost. Given two candidate location, if you deviate from the edge that belong to those two targets, you're going to pay more penalty. And in order to make it PSD, we're going to use the same trick. So given the affinity measures, the objective function, now the question is that how do you solve this? Probably the first option is to use available quadratic programming solvers such as Cplex and MOSEC. But what we observed is that we observed that the computational complexity and also the runtime is too high when the number of targets increases. You can see as we reach 200 targets in the sequence, it takes more than 20 seconds to solve the optimization, which is not what we want. So what we do instead, we use another technique called Frank-Wolfe algorithm. So this Frank-Wolfe algorithm is used to solve constraint convex optimization, and it's gained a lot of attention recently in machine learning community. The idea here is that instead of considering the original problem during minimization, you consider a linearized version of the original problem. In our case, a linearized version is going to require solving a linear programming, while the original problem is quadratic programming. So solving LP is much easier than solving QP. Here's the idea. We want to minimize F. You can see the function f here subject to convex set D. So for regular gradient descent method, let's say the current iteration, the solution is x, you would compute the gradient, you would move toward the negative gradient direction. But what Frank-Wolfe is going to do is that it's going to approximate the function at that location with its linearized version. And its linearized version is nothing but the first order Taylor approximation of the function at that point x. So this is the equation of the linearized version of the function, which is defined by GS, and it's shown with this red plane. So instead of considering the blue, you're going to consider the red, and you're going to minimize over the red plane. You're going to find a new location, S, and you're going to move toward the new location until you converge. Here is the detailed Frank-Wolfe algorithm. Again, it's an iterative optimization. You initialize your parameter. This is the linearized version of the objective function that you solve, and this is the solution that you get. This is the Frank-Wolfe direction. Basically, this is the direction that you want to move toward. But now the question is that given the new point, how much do you want to move toward the new point? This requires solving another optimization, another line search problem that is not always easy to solve. But in our case, this line search problem is going to have a closed form solution, which is shown here. So we can easily find the optimal step size at every iteration in our problem. And once we get the step size and we have the new direction to move toward, we can update x as shown here. So at the end of the iteration, we're going to get the final solution that is found by Frank-Wolfe, but remember that we had to relax the binary constraint in our optimization. So the solution that Frank-Wolfe is going to give us is going to be any variable, any values between 0 and 1. So we have to round this solution and make sure that the final solution is going to be binary variable because we want it to satisfy the first constraint that we define in our objective function. This requires solving another optimization. Z is the rounded solution. You want it to be close to what Frank-Wolfe has found for you, but at the same time you want Z to satisfy the constraint that you have defined in the beginning. So in our case, this reduces to solving the optimization for each target separately, which is not very difficult. So we talked about Frank-Wolfe, but there's a problem with Frank-Wolfe. When you get close to the optimal solution, the convergence rates slack. So it starts to showing some zigzag effect. That's why people introduce modified version of Frank-Wolfe, such as Frank-Wolfe with a wave step. And what we use here is the most recent version of Frank-Wolfe algorithm, which is Frank-Wolfe with swap steps. Here's the detailed algorithm, but the main difference is shown here. And what happens here is that instead of just finding the descent direction, which was the case in Frank-Wolfe, you also find the ascent direction over the previously seen atoms. For example, if you're at iteration number 100, this optimization is done over the 99 previous found atoms. Now you have two directions that you want to move toward. So you have to find two line search problem. The first line search is over this direction, which is the original Frank-Wolfe direction, and the swap direction is defined by sk minus yk. And once you find solve the line search, you want to select one of them. You want to see which direction do I want to move toward. And what you do is that you look at the improvement of function at every direction. The direction that is going to give you the better improvement is going to be selected as the new direction that you want to move toward, and you want to update your current solution. Now I'm going to show you how it affects the runtime. This was the runtime for Cplex, and this is the runtime for Frank-Wolfe with swap steps for different duality gap values that defines the accuracy of your solution. So you can see that now we can find a solution which requires a lot less time compared to Cplex. For experiment, we use 9 high-density sequences. You can see the details of these sequences here. There are a lot of number of targets in most of the sequences. And we also annotated 2 new sequences, which are medium crowd density, to show that our method also works for medium crowd density sequences. Each of them has 2,000 frames. In the first one, we annotated 200 targets, and the second one, we annotated 215 targets. Let's have a look at some qualitative results. This is one of the sequences in our data set. You can see that targets look very similar, and on the right, you see the close-up version of the target to see what's happening actually. And here's the quantitative numbers we compare with 6 other methods. And this is the pixel threshold, and this is the tracking accuracy. On the left, you see the results, and on the right, you see the curves. And you can see that our method does better compared to other methods. And this is another sequence, which is a marathon scenario. Again, there are a lot of targets in it that look very similar. It's very difficult to track all these targets at the same time. Our method does it quite well compared to previous methods and achieves better results compared to previous methods, which is shown in this graph here. Now, we're going to fix the pixel threshold to 15, and we're going to look at the numbers. We're going to give a closer look at the numbers. Here is the results. You can see that on the first 5 sequences, we improved the numbers compared to other methods. And this is the other 4 sequences. For most of them, we improve. For some, there is not much improvement, but in average, we improve by almost 6% compared to other methods. And this is the medium, one of the medium crowd density sequences, and these are the qualitative results on that. And you can see the quantitative results for both sequences. On the left, you see the tracking results, and on the right, you see the tracking accuracy with respect to pixel threshold error. And we are comparing with NMC, which is the work of Idris et al., which was the state-of-the-art before this method. And at the end, I'm going to show you the contribution of each term that we proposed in our optimization. If we use a baseline tracker, let's say we use a baseline and we only use a generative tracker based on normalized cross-correlation, this is the number that we're going to get. If we add motion, we get slight improvement. And one thing I want you to notice is that this baseline is the same baseline that was used in the work of Idris et al., but the average performance is almost 30% higher. And the only difference is here that we are using joint optimization. This shows that using joint optimization is very essential. It gives us a baseline that is 30% higher than previous methods. Using spatial proximity constraint, we get improvement in almost all sequences. Grouping constraint gives us slight improvements in some of the sequences, slight improvement coming from neighborhood motion. And once we replace the generative tracker based on normalized cross-correlation, with a discriminatively learned tracker, we can further improve the results. In summary, in the first part, we proposed a global data association method based on generalized maximum clique graph. We incorporate both appearance and motion in a global manner while solving the optimization for one target at a time. In next part, we propose a modified version of GMCP, which is called GMMCP. We also incorporate appearance and motion in a global manner, defines all the cliques at the same time, and we propose an efficient occlusion handling through ADNs, and we propose a mixed binary integer programming solution for that, and we show that the optimization is quite fast. And in the last chapter, we propose a flexible tracker that is capable of tracking hundreds of targets efficiently, and we propose an optimization which is based on Frank-Wolfe that is also quite fast. For future work, one direction would be to use nonlinear motion model instead of linear motion model. That is important when dealing with sport sequences. And also, if you have a nonlinear underlying motion model, you'll be able to increase the temporal span during data association, which you eventually will be able to better deal with occlusion. We can use better features. We are just using appearance feature here, but deep learning feature is another direction to discover. More efficient optimization for GMMCP. GMMCP does very well when dealing with sequences where we have less than 30 targets in it, but as the number of targets increases, the runtime also increases. For crowd tracker, one direction is to increase the temporal locality, which means that we consider more than one frame during data association. Right now, the runtime is going to be too much if we do that, so it's not feasible given the available solver we have. We can add scale handling. Sometimes you have perspective effect, and right now we don't have scale handling that can potentially improve the tracking, and we can also improve the underlying tracker. So there are much better discriminatively learned trackers that due to their computational complexity we are not able to use in our current pipeline. And at the end, I'm going to show you a list of papers that I had during my PhD. I worked on multi-object tracking problem. These 4 papers are the papers that cover the content of my dissertation. I also worked on content-based video analysis, and I also worked on some other problems such as kinship recognition and visual business recognition. I also had the honor to be involved in a lot of projects here. The results are in some technical reports. And at the end, I want to thank you for listening, and I also want to thank all the people whom I collaborated with during my PhD. Thank you.